This podcast was produced from a webinar. For a more interactive experience with visuals, visit advancedmanufacturing.org/webinars. Welcome to another SME Media webinar. I'm Carrie Gitter, Associate Editor. Today we'll be exploring the topic Advanced Machining Strategies for Solid Carbide Milling. This presentation is sponsored by CERATIZIT Group, and we're joined by Scott Walrath, Business Development Manager at CERATIZIT. Now it's my pleasure to turn things over to Scott. Welcome. We're happy to have you join us today.
Oh, thank you. Thank you very much. Happy to be here. Okay, everyone. Just a brief introduction of myself. I've been in this industry 42 years now. And the amazing part is it's always been focused around end mills, not always solid carbide. I am kind of dating myself when I say that. Solid carbide really evolved right around the mid 80s, late 80s. When I actually started in the early 80s, we were still dealing with high-speed and cobalt end mills. And then carbide really came on strong into the scene in the beginning of the 90s. I did spend a fair amount of time making end mills. I spent about 3.5 years in the shop programming CNC machines, which were a lot different back then than they are today. And a lot of my job responsibilities have always been focused on, tool design, looking at substrates, looking at microgeometries, the edge rounding, edge prep, call it what you want, with the tools and coatings and how those all match together. So 42 years of doing this. It's been a great pleasure, and I'm happy to be here. Hopefully, I can provide you with some tips moving forward, and I'll kind of go over the outline for today. It's kind of broken up in 4 segments. A lot of you may not know who CERATIZIT is, so I'm going to do a little bit of introduction of CERATIZIT, our core beliefs, our passion. We'll do a little bit of an intro into how we approach the solid round tool market. From there, we'll transition to tips for good end mill performances and optimization. And then we'll get into really the meat and potatoes of the strategies that this meeting has been focused on. And then we'll follow up with a Q&A. So again, thanks for being here, and let's go ahead and start. So CERATIZIT, essentially, we're a tooling company that has a passion. We believe in a sustainable future. We are a high technology engineering company that specializes in cutting tools and hard material solutions. We have multiple plants globally. We have several plants in Germany, one in Austria. We have 3 manufacturing plants in the United States, one in India, just to name a few. Moving on to the slide. There we go. All right. So again, who we are, we have a full complement of cutting tool solutions, whether it's a solid solution or an indexable solution, whether it's drilling, milling, turning, solid or indexable, we have a full complement of cutters. Into the hard material solutions, of course, we get involved into rod, cut to length rod, ground rod, all different types of carbide wear parts, inserts, hob gearing cutters, and so forth. Who are there for? End users, OEMs, tool makers, and we do quite a bit with private label for other manufacturers. Our application areas are automotive, mechanical engineering, construction, medical systems, aerospace. We have a high emphasis in aerospace, consumer electronics, energy, and if I had to add one that's not listed here, agriculture. So the raw material supply, this is one of our passions for a sustainable future. The use of secondary raw materials and scrap production. We do believe into recycling for that sustainable future. All our materials are sourced from certified and audited mines with a high environment and social responsibility. Our goal is, again, to reduce the scrap and recycle it. We have a big focus on helping out our customers for a suitable material solution and economically or ecologically produced processes. Okay, so we are one of the world's largest carbide grade manufacturers. We have over 100 different carbide grades, particularly for wear parts, cutting tools, and we have basically a grade for every customized solution. Our approach to the solid carbide tools, we look at it in two ways. We have a universal approach, which is essentially a very versatile offering that covers 90%, probably even greater than 90% of the majority of the applications out there, which basically offers a high end of versatility and giving you very good high performance throughout the range. This offer will be very broad in base in terms of product SKUs. They are very large in terms of full range of diameters, from very small diameters to large diameters, different styles, different lengths, different radii, all geared towards applications that are very broad based, that covers the full spectrum of the ISO materials, whether it's ISO P, ISO K, ISO M, and so forth. Then we go into an optimized approach. This is where it becomes more material specific and application specific. This is where we go and we drill down deeper, where we look at the four main components of the end mill. Essentially, we're looking at substrate, we're looking at coating, we're looking at the microgeometries, the geometries of the tools, and bringing it all together. So if we were to do a deeper dive on this into the optimized, we came out with a series, a 6-flute series, that was really, we followed the same principles that you may find in the auto racing industry, where they look at balancing and blueprinting, and how we took those same principles and applied it to our end mills, so that everything is, meticulously engineered and in balance and in a cohesive and coherent state. For instance, if we look at, bear with me. So if we look at the four main attributes of a cutting tool, right, which again, substrate, geometry, edge prep, and coating, everything is, meticulously engineered to create a balance and, to get optimal performance. So we'll do a little bit of a deeper dive into the substrate. So when we came out with our ISO-S tool, we essentially used a very unique grade of carbide. Here we used a carbide that had a very high fracture toughness, probably about an extra point or two higher than the normal, right? Without really sacrificing the hardness. The hardness runs around about 91.8. So we only lost about 0.2 of the hardness. But what we got in return is we got enhanced ductility for the tool. And if we see how normally tools, wear, we don't live in a perfect world. These tools typically kind of chip away, and very seldomly do we see even wear throughout the cutting edges. So we really have picked up an essential, component with added ductility. This allows us to be a little bit more aggressive with the cutting edges because we do have increased ductility. Because of the fine grain structure, it also allows us to manipulate the edges when it comes to edge prep. So when we do a deep dive into the geometry, we have applied a asymmetrical flute configuration coupled with a irregular pitch with the flute spacing. What this allows, it gives more stability throughout the part. So all the cutting angles are attacking the workpiece at different angles. There is no commonly shared helix angle. This creates added stability to the cutter, which again, reducing harmonics. We have furthermore optimized the cutting relief angles engineered for ISO-S materials such as titanium alloy and nickel-based alloys. Because of the finer grain size, we're allowed to have a little bit more precise cutting edges, which is very, very important when cutting ISO-S materials. We don't want to overcompensate and have, large, edge rounding to the corners. So with the fine grain structure, this allows us to have very sharp, homogeneous cutting edges. This process is highly controlled. It's not batch manufactured. It's done one at a time, and it's measured. Each tool is measured and qualified to the specific requirements, ensuring maximal and predictable tool wear. Our famed dragon skin coating is a multi-level layer coating. Can go up to 2,000 layers of coating. And we're only, again, when we're looking at total thickness, we're looking at, relatively on the larger tools around 3 microns on the thickness. But within that, there are many, many nano layers of each coating. This allows a feature called, crack stopping structure, which prevents it spreading throughout the cutting edge, which presents longer tool life to the cutter. Just to give you a little bit of some of the components and features of the cutter, we are looking at a Vickers hardness around 3,800. Again, the thickness of the coating is relatively thin because we do not want to create a very large edge rounding to it. We don't want to compound it because we're already edge prepping, and now we're putting a layer of coating. So we like to keep it very, very thin. And it has a thermal stability of around 1,000 degrees Celsius, which is relatively a little over 1,800. I think it's 1,832 degrees Fahrenheit, which is pretty stable. You can run these tools dry and they hold up very, very well. Okay, so going into now into more generalized approach, right? So this would apply to not only our tools, but tools in general, right? So if you're looking to optimize, right, your machining, your end mill performance, we always recommend, go through the catalog. If you're using us, great. We would love to have you as a customer, but go through and see what's suitable. Let's for instance say that you're machining titanium. Well, go through the catalog and find to see if they have tools for such materials. You want to go ahead and say, well, I want to HEM, a high efficiency milling operation for titanium. Then we, go through the catalog, look for, hey, this is a preferred choice. A lot of the companies, such as ourselves, will have a preferred choice and a suitable choice. When you make that extra effort to go with the preferred choice, those tools have been engineered specifically for those materials, and we encourage you to go ahead and use those tools because things may be more, a deeper dive. So, right, the substrate may be more engineered for that, right? The helix angles and the cutting angles are more engineered for that particular material. If there's any edge prep, those are probably most likely engineered for those materials as well as the coating. So we always encourage to go through the catalog, and if you don't see it, call the manufacturer and ask. They will guide you for it. So we'll move on to the next slide. Also, too, know the limits of your machine tool, right? You should know, your horsepower rating, your RPM range. It's always good to know the part that you're machining, know the orientation of your spindle, which I'm sure you do, but how are those chips going to fall, right? If you are, machining, if your spindle is horizontal or vertical, you need to kind of calculate and say, well, I could have a potential chip problem because the orientation of my spindle and the nature of the part, there may be pockets of chips in collecting. So you want to take that into consideration. Also, too, what I find most important, and this, again, we seem to be very focused on machining titanium and iso-S materials, know the taper size. So if you have a 40 taper machine and you want to go ahead and say, well, I'm thinking about, using a 3/4 inch diameter end mill to machine Inconel. Well, you may want to rethink that, because really the threshold for that would be right around a 1/2 inch. You could maybe go, 16 millimeter or 5/8, but understand that there could be limitations on how fast you could run that tool, and, what type of tool life could be diminished by going to a larger tool. So always kind of know the parameters of your machine tool. Furthermore, understand the capabilities of your CAM software. Do you have HEM capability? Can you trochoidal mill? Does the software have chip thinning offsets? Does it have chip thickness monitoring capability? And I could spend a whole segment just going over radial chip thinning, which is highly important. But these are important factors that really need to be taken into consideration, when making choices on selecting the right end mill. Also, taking consideration of the fixtures, right? Do you have a pretty rigid, setup? Is there going to be vibration? Also, you want to take in consideration of what type of milling operations that you will be performing. Is it one or is it multiple? If, again, referring to most end mill manufacturers' catalogs, they'll have icons, little pictograms of telling you what these tools are capable of doing. Whether it's, yes, I can ramp, I can helical ramp, or I can circle interpolate. This is good for slotting. This is good for plunging. Plunging, it's going to have to be center cutting, and so on. So try to make a determination of saying, well, I can do everything with one tool if I do this, or if you need a series of tools. And again, always, look for, to the manufacturer on what they can, provide and what they recommend. Okay, I put together kind of a guide here for flute selection, because this comes up rather often. So when we're considering flute, or otherwise known edge count, right? Because it's the flutes that don't do the cutting, it's the edges, the cutting edges that do. So if you're doing a heavy roughing, whereas the radial step over is you're immersing that cutter 50% of the diameter, you pretty much want to go with a 4 flute. You may want to consider if like a knuckle form rougher, or even a rougher finisher, to help augment that chip management. If we're doing a moderate adepta cut, which is I have that listed as about 25% of the diameter step over, here we want to consider going with a 4 or a 5 flute. When we look at light milling, which is about 20% radial step over, here we go with suggesting a 5 or a 6 flute. So again, with the slotting and plunging, we always want to go with 3 or 4. Finishing, which is typically about 10% of the diameter, we can go 6, 7, and now you can probably go to 8, 9, 10, 11 flutes for that consideration. And then when we look at high efficiency milling, HEM, where we're now looking at 5 to 10%, you at least want to go with 5, and you can go to an infinite amount of flutes. I know there are some cutters out there that have 9, 10, 11, 13, and so on. Those are the tools that you really want to consider for maximal metal removal rates. And then trichoidal, which we'll be going over shortly. Typically, this is about a 7% radial step over. Here we want to look at right around 5, 6, or 7 flutes because, again, we're going to use an end mill going into a pocket area or a slot. So we don't want to get too heavy with the chips. We want to make sure that we get good chip evacuation. So 5, 6, 7 flutes seems to be, the way to go for that particular operation. Furthermore, when we're considering, tool selection, I always like to go with the maximal diameter as possible. This is going to give you added rigidity to the tool, stability, and all in all, yes, you may pay a little bit more up front for a bigger tool, but in the long run, you are going to pay for it. You're going to get a payback to it. As I mentioned before, and again, this is very, very important, is that when we, start to consider, machining super alloys, if your machine you're planning to doing on a light machine that has a 40 taper holder, right? You may want to kind of limit your diameter range to not exceeding a 1/2 inch for optimal output. Length of cut, be sure don't be using extra long length of cuts if you're not going to utilize it, right? Because we want to keep it as short as possible and as rigid as possible to maximize that rigidity, and you'll get a payback in return with extended tool life. If you have to reach down into deep cavities, rather than using a long length end mill, a long length of cut end mill, use an extended reach. If you need a neck relief, then use a tool that has a neck relief to get inside that cavity. That is actually going to help you with, again, extending your tool life, as opposed to using a tool that's been fluted, 3-4 inches up the flute, and you're using the end mill, just because of the length. Use an extended reach. Lastly, and use quarter radiuses, for that edge protection. That's always a benefit as well. Okay, moving into some common mistakes and failures. I felt important that this is we bring this up, right? So when we have a failure, the end mill is always the first to blame, right? So essentially, what's really, really important is to make sure that the tool holding is at its optimal, right? We want to make sure that you're using, a good tool holder. Hasn't been, it's clean. It doesn't have any chips in it. It hasn't been subjected to a crash. So that's very, very important. You have to understand that carbide relatively, right, is right around 92 Rockwell. It is very hard. It is very, it tends to be brittle, right? And so it's really important to provide a stable environment, right, for solid carbide end mills to thrive. Doesn't matter if it's a CERATIZIT end mill or somebody else's end mill out there. It doesn't matter what geometry or coating. It's, we are all subject to, we need a stable environment. So try your best to make the environment stable, whether it's through the fixturing, whether it's through the tool holding. Keep in mind, which I think is a very important fact, is that, check the run out regularly. You really should be, with the tool in the holder, right? What's optimal, check it, and put a drop indicator on that and say, what, I'm at, the target is 3/10. Could you go 5/10? Yeah, you could, but you really don't want to exceed that, because keep in mind, for every 1/10 of TIR, you're going to lose about 10% of tool life. So TIR is at the utmost importance when you're looking, when you're running solid carbide end mills. Okay, a little deeper dive into how, into tool holding and end mills. Okay, so again, some of the usual suspects, right? Spindle, taper conditions, drawbar, backlash, the tool holder. Make sure you're using, relatively new tool holders. If you guys go ahead and spend a lot of money on a high performance tool, do yourself a favor and do the end mill a favor and use a high end, tool holder. again, it's the payback is going to be huge. Again, the goal is to minimize the TIR. And lastly, what I have on this illustration is, again, I do see this a lot when I walk into shops, and I don't know, this is not really expressed enough, but it should be. Ideally, you want a minimum of 2 times the diameter back into the holder, right? Preferably be about 2.5 times. Somewhere if you can fall in between that 2.5, you're going to get that. The payback is huge. You're going to get more stability with a cutter. You're going to have achieving better TIR, with that tool into the holder. All in all, it's a huge payback to yourself for, optimizing your milling operations. Okay, so here I put this illustration up because there's still I find that there's a lot of side lock holders out there in the industry. Back about 20 years ago, I thought maybe the side lock holders would go away, but there really has been a resurgence, and kudos to the tool holder manufacturers. Some of the side lock holders out there you can get with very tight TIR, high accuracy. I think you can get some with about 1 TIR guaranteed. That's great. I would encourage you to use those when you're using a high performance end mill and when you want to go ahead and optimize. I did put this illustration up because this illustration is ANSI B94 for the Weldon flat. Now, the important thing is this ANSI B94 was established a long time ago, probably 30, maybe close to 40 years ago. And it was based not on carbide, it was based on high speed. As we were evolving from high speed into carbide, I wish the rod manufacturers and the tool manufacturers got together, because essentially, and I'm going to pick on the half-inch tool on a high speed or a cobalt end mill is the typical dimensions for a standard length is a 1/2 inch diameter, 1/2 inch shank, 1.25 inch length to cut with a 3.25 overall. So if you look at this illustration, the center line of the flat location, the V dimension, is all based on the back end. So typical rod for solid carbide are, most of us, and I think there may be a few that go with a 3.25 overall, but most rod manufacturers and most end mill manufacturers have a 1/2 by 1/2 by 1.25 by 3. So we have to keep in mind when we're placing the Weldon flat, how that may look like when you put that tool into the holder, right? So we want to make sure that, depending on the holder that you're using, we want to minimize that flute wash that goes into the holder. And I'll go to the next page and we can kind of look at some of the things that we want to be mindful of. So location is very, very important. So if you're looking for an end mill, and some tool manufacturers do offer Weldon flats as a standard, it's always a good idea to ask them the placement of that flat, so and kind of match that up with the tool holder that you're going to use. Because what you want to minimize and eliminate is you want that flute runner, the flute run out. You do not want that to go in the holder, because what happens there, I've seen it time and time again, where if you're reaching, if you're utilizing that full length of cut, the chips seem to want to go up into the holder, which is not a good situation. So again, I'll go back to whereas we want a minimum of 2 times the diameter back into the holder. Here's another thing that we were troubleshooting back in my previous job some years ago. We had some breakage, and we couldn't figure out why we were breaking tools. And then we found out, and I'm just going to go back to the previous page. So someone was using NAS 986 set screws, which the 986 standard, which is an aeronautical inserted the screws into an ANSI holder. And what happened was that W dimension on the ANSI set screw is larger. That W dimension on the screw is larger than the W dimension on the flat. So what happened is that set screw was riding on the two angles here, and essentially, any type of tool pressure, it was breaking the tool. So be mindful if you're using set screw into your ANSI holders. Just make sure that they're ANSI set screws and not NAS to eliminate that problem. Okay, now we're going to go into the strategies of the advanced milling. So we're going to talk about basically three main strategies. Trochoidal, which you guys may have heard of. It's become very popular. Essentially, it's a efficient way for producing slots, a series of slots. And essentially, it uses a circular cutting motion and puts less wear into the tool. HEM is really, again, HEM and trochoidal is almost of the same principle, where you're utilizing a minimal radial depth of cut, but you're engaging the cutter up the entire axis of the cutter, which now you're dissipating some of that heat and you're getting, maximal metal removal, because the feed rates that you're going to run these tools at is much, much greater from a traditional type of cut. And then we're going to go over circular ramping, aka helical interpolation, and then we'll go over a full slot milling versus a trochoidal method, because I know some people don't have the capability of doing trochoidal, and some I made some pointers that if you are going to full slot mill, give you some pointers on how to do that effectively. So here we're going to talk about the trochoidal milling. So again, it's circular milling that's got simultaneously forward movements, right? So it's a series of slices, right? We're going to go into a slot area. Typically, if we were to use a 1/2-inch end mill, you could typically go up to about a 1-inch diameter slot, right? You want to use about 50% of the diameter of the tool. If you're going to mill a 1-inch slot, then typically about 50% reduction of the tool, so a 1/2-inch tool would be utilized, right? You have to have the proper CAM software to be able to use this method. Furthermore, you need to use the proper tools to use this method, because as you can see in the picture, that cutter is fully immersed, and we have to have some form of chip breakers to manage that chip. And down below, you can see some diagrams that kind of show the tool path on how this method is done. Next up is a video showing the illustration of how this is done. Okay. And I think we're back on to this screen. Let's just review the benefits of the trochoidal milling. As you did notice that the color of the chips and the trochoidal maneuver, you can see that the chips were very blue, which is a good thing to see, because all that heat is now dissipated into the chip rather than the cutting tool, thus leading to longer tool life. So let's just review the benefits real quickly. Again, you can immerse up the axis of the cutter. You can go 5 times D as possible. We reduced the machining costs thanks to the significant increase to the data, to conventional machining. The short chip breakers help, maintain that, the chip management. We generate low heat because of the short contact times into the workpiece. Extremely high feed rates, right, due to the small width of cut. It's a highly process secure machining strategy. Low machine loads due to the low depths, of the radial depths of the cutting tool. And again, there's no localized wear where, if you're doing step downs where you're, looking at, notch wear up the axis of the cutter, that whole, the whole length of cut is engaged in the cutter. So you're getting more even wear. Okay, so we're going to do a little bit of a comparison. The trochoidal strategy versus a full slot strategy. We already went over some of the benefits of a trochoidal maneuver, but when we do full slot. And I will say probably about 15 years ago, right, there was a buzz on, having end mills being able to slot, 1 times D. This was basically prior to trichoidal type of, maneuvers were popular. So a lot of tool manufacturers were chasing this, whereas, hey, can we produce, tools that are able to do this? I don't know how relatively it's used today. It can be done, but please keep in mind that if you do choose to do this, I did make some pointers that are very important. Again, I'd like to see you use 3 to 4 flutes would be preferred. A taper core would be a must, and this is for helping the chip evacuation going up and extracting it, because you don't want to be recutting chips. And also the gashing needs to be right. I'd like to see wide open gashing with nice blended radii. We don't want any sharp transition points in the gash because they'll have a tendency to collect and bind up, and that's not a good situation. And as always, ask the manufacturer. I know there's tools out there. We have a tool out there that can do 1 times D slotting. Again, with trichoidal now coming onto the scene, it's a much preferred technique as opposed to 1 times D slotting. But I know there are people out there that still like to do it. But again, ask the manufacturer and ask if they have a solution for it. Okay, now getting into the HEM. Essentially, HEM is just quite the opposite of a traditional mill, right? Where traditional milling would always incorporate a heavy radial depth of cut with a relatively shallow axial depth of cut. HEM kind of flips the approach. We basically are now saying, if you go with a light radial depth of cut and then increase the axial depth of cut, we then can now basically increase the feed rates much higher, thus creating a higher metal removal rate. And essentially, by spreading the axial engagement of the end mill across the workpiece, we dissipate that heat, effectively reducing thermal stress, and then essentially increasing tool life. Moving on to the next slide. Some guidance on HEM. Again, check your manufacturer's tool selection guide for proper tool selection. These tools are generally 5 flute plus. You could, again, there are manufacturers were coming out with a 9 flute shortly. You want to at least use the 5, 6, 7, 8, 9, 10, infinite amount of flutes. You're just going to have to adjust accordingly in terms to your radial step over, right? Use a variable pitch, all right, and variable helix. Preferably, ours is asymmetrical. We're real big on that. That has a, going with an asymmetrical design, reduces the harmonics probably by 20% over a more, typical symmetrical variable helix. So if you can go with asymmetrical variable helix, I encourage you to use it. Also, tools with edge prep. Our tools, all our high performance tools come with an edge prep. Ask your tool. If you're not using our tools, ask your manufacturer, how they're edge prepping, if they're edge prepping, and how they're edge prepping, right? We use a very consistent, very refined edge, and ours are very, very controlled and highly qualified. So it's very important that, the edge, the cutting edge is the first, contact into the workpiece. So we find the importance of edge prep is critical. And again, also, choose the appropriate coating. Again, I would always refer back to the manufacturer and saying, hey, you guys make tools for HEM, then hopefully they can guide you accordingly. Here's a scenario in terms of what HEM can provide you versus, a traditional mill. For instance, and this has actually been done and tested. So it's really not a potential, it is actually actual. We used our 1/2-inch 6 flute OptiMill, OptiLine mill into titanium 6AL4V We did a comparison of light roughing, where we engaged the radial step over, what we typically would do, 20%, 100,000 radial step over, and going up we have to be limited on terms of our axial depth, which was 5/8. We fed that at a little over 2.5 thou, which gave us an actual chip thickness right around 2 thou. You could add to that if you wanted to. You'd get a little bit of a bump up for radial chip thinning. But when we look at an HEM maneuver, and you can go 355, I've actually gone up to 400 on titanium and milled it quite effectively, and based it on a 5 thou chip load. And essentially that's going to give us a little just under 3.5 thou chip thickness, which is really kind of ideal to have. And you can see that the huge difference in the cubic inch removal, the metal removal rate, jumped from 2.1 to 6.4. So there is a significant increase of productivity. Okay, the last strategy we're going to talk about, and I know we're getting close on time, how quickly the time is going by. We're going to look at helical ramping. Yes, there is some standard ramping, linear ramping, where, we make entry into the part, but we want to do a little bit of a helical ramp, talk about that. Essentially that, a lot of people essentially were removing the step of pre-drilling, and we could go enter into the part utilizing this type of technique. Again, you have to have the software to be able to do this. It involves both all three axes, X, Y, and Z, where it distributes the load over 3 axes of the cutter. And essentially by doing that, we're going to extend tool life, lower the vibration, faster machining, smaller chips, and less tools into your carousel. So if we can reduce the tool count in the carousel, that's also a benefit. Here are some typical speeds and feeds that I made for the ISO S class. ISO S3, which would be nickel-based alloys, for example, Astalloy, Inconel, Incalloy, Bonel, Waspalloy, and such. The ISO S titanium alloy, commonly 6AL4V. Essentially, if we look at some of the feed rates here, we're looking at for titanium, 2 thou to 2.5 thou, feed per tooth, and running that around 100 to 120 SFM. We do have some real world results from an aerospace engine manufacturer. This was a helical ramp mill, a series of 18 holes per part and 718 Inco. It was a tube. They were running 80 SFM at just over 2 thou chip load per tooth, which calculated a little over 7 inches a minute. Their Z depth per cut was 16 thou. And the results, and mind you, this was a 6 flute doing a helical ramp, circle interpolation. We got 9 parts with even wear, about 8 thousandths flank wear, even wear, both on the flank and the radii. Whereas the incumbent tool was a 4 flute configuration, and we increased the feed rate by 35%. And just kind of wrap things up, our industry focus, we're heavily into aerospace components, oil and gas. We just had a great success with a dog bone coupon milling component. Some details on that to come on the success story. I'm sure we'll post that up somewhere for you guys to review. We're into automotive, medical, and much, much more. And we're looking at the supply chain, again, to kind of wrap things up. Our emphasis on, again, sustainability. So we have this closed loop of recycling, right? So our emphasis is on availability of rod, from powder to rod finish. Basically, we want to ensure, sustainability and constant performance. Global production enables us scalability and repeatability. I'd like to thank everyone for their time. I will be attending the upcoming shows. I will be at Saltech actually next week, And then a couple of weeks thereafter, I'll be at Hustex, which is actually in Dallas. And if you are there, please stop by the CERATIZIT booth, and I'll be happy to talk to you and answer any questions you may have. And I thank you so much for your time. And wow, did we really go through some time? So
great, thank you, Scott.
Yeah, you're welcome. And hopefully we got a little bit of time to answer some of your questions.
All right. Well, thanks again for such an insightful presentation. And yes, it looks like we have received some questions from our audience. Quick reminder to attendees to get your questions in while we still have Scott here on hand. So let's get started. Here's one. What are the most important factors to consider when selecting a tool holder for an end mill?
Okay, great question. So there are definitely an array of holders. I personally like mill chucks. I like hydraulic holders. It really depends what you're using, or what I should say. It really depends on what you plan to do. If you plan to rough, right, mill chucks are very, very good. Again, I'm not opposed to side locks, providing that you use a high precision side lock and that makes sure that the flats that they're machine ground and that the location is proper. HSK is another great way of for mill chucks. Shrink fits. I know some people use shrink fits. They are fine, but I would be very careful to make sure that your tools have a matted finish, not a very high polished finish on the shanks, because that could lead into some gripping problems.
Great, thank you. Here we go, another one. Why does substrate play an important role in optimization for tools?
Yeah, great question. So substrate is what we do is that, again, what we did with our 6 flute, if you understand what the substrate's for, it's truly the foundation of the carbide. And if you have a total understanding of what that substrate can provide you, like we did with our 6 flute, we were able to go very, very aggressive, right? This is designed for ISO-S materials. We were able to go with high rake angles, high relief angles, because of that substrate, because of that, of its nature of being very high fracture toughness. And again, I would take a higher fracture toughness over hardness any day of the week, because how most tools fail is, they typically chip out unless we're working in a lab environment and everything is, tightly knit, and everything is under control. Then maybe you would want to consider a tool that has a substrate that has a higher hardness. But I not knowing where these tools are going to be applied and housekeeping and people's, capabilities and whatnot, I always like a substrate that has a higher fracture toughness.
Great. A couple more just came in. How does the depth of cut and feed rate affect the wear of the milling tools?
So if you are, for instance, if we're using HEM or trichoidal type practices, that cutter is, we're now putting the heat into the chip. As we look back into the trichoidal video, we saw that on the left-hand side, which was traditional milling, right, versus the trichoidal, you could see that the chips for the trichoidal were very, very blue. So the heat dissipated into the chip rather into the cutting tool. So it's got an in and out phase. It doesn't stay in it very long, and that's what you want to try to accomplish.
Terrific. And do you ever run into issues with galling? If so, how do you combat that?
Galling. Okay. So if you have galling, I would, again, I would look into how that cutting edge is presented, right? Take in consideration of the material that you're machining, the tool that you're using. Make sure that you have a very, very sharp cutting edge. If there's an abundance of edge rounding, always check with the manufacturer. You can actually run your finger up the tool, and say, "Ooh, boy, that has a significant amount of edge rounding." Put it up on a microscope, look at it. You want something that's very sharp, and then you're going to have to adjust accordingly with speeds and feeds to eliminate that kind of condition. You also may want to look at, are you, experiencing some type of radial chip thinning as well?
Great. And this just came in. Just curious, why are axial and radial depth of cuts referred to as AP and AE?
Okay, so that's a really good question. I'm not really sure. I think that was a European nomenclature that used it, but that is universal throughout the industry. AP being for the axial and then AE for the radial.
Great. Another one here. How do you deal with fracture of tools in end milling operations? What do you look out for to rectify tool fracture?
Okay, so again, I would look at, you'd have to do a deep dive into where the fracture occurred. Okay, I think as I mentioned earlier in the broadcast where we were troubleshooting, this goes back about 10, 15 years ago, we were troubleshooting, we had fractures up in the shank, they're breaking off into the holder, and we're like, wow, this is, how is this happening? And we kind of identified, well, it was a tool holder problem. It was the set screw flat that was resting on the angles of the flat, and we weren't getting a secure lockdown. So, but fractures can, not only from flats, but it could be, use of the wrong tool. It could be, that the speeds and feeds, the cutting parameters. There's a lot going on. What's really important is to collect the tools. If it's fractured into 2 pieces or 3 pieces, collect the tools and send them off to the manufacturer. Give them the cutting data, give them the milling operation, and hopefully they can, troubleshoot and kind of determine what happened and what went wrong.
Got it. Here's a good one. Is there a good modern reference resource for speeds and feeds, or is contacting the manufacturer the only way?
I would say, probably the manufacturer is probably the best choice. And every manufacturer has speeds and feeds. Some have calculators. They're generally within the same, they're relatively close within each other, right? Unless we're looking at more optimized tools where they've done a deep drill down into a specific material or machining application where they have everything dialed in. There may be, for a general one, they may want to check the CNC cookbook. He may have some general information on machining parameters. I know there are some good parameters out there, but I think the CNC cookbook guy that does that publishes that, I think has some good generic speeds and feeds for everyone to use.
Great. Okay, lots of good questions here. I'll just put out a last call for any last minute questions for Scott before we wrap up. And again, you can always watch the webinar after the fact, and Scott's information will be available as well. All right, looks like we're all good. So Scott, want to thank you again. Go ahead.
Oh yeah, no, I want to thank everyone. Everyone's got, they're busy with their schedules, and I hope at least maybe, you gain one or a couple things you can take away and give you some benefit to better end milling and so on. And we'd be more than happy to help you as a customer. But we know you guys have options out there. And as I always say, always rely on the tool manufacturer. They know their tools the best, and for guidance. But again, thank you for your time.
Thank you, Scott. And thank you to CERATIZIT for sponsoring the podcast and joining us today and sharing this very informative and useful presentation. Also want to thank our attendees for your participation and all those great questions. We hope you found this content valuable and will join us again soon. Until then, remember that SME Media are here to help you stay up to date on all things manufacturing. You can find links to podcasts, webinars, publications, and news by visiting us at advancedmanufacturing.org. Thank you for tuning in.